Bioethanol production from agricultural waste like corn stover is important because it offers a sustainable alternative to fossil fuels, especially for internal combustion engines. Corn stover, the husk, stalks, and leaves left after corn harvesting, is usually discarded, but it can be converted into bioethanol, reducing waste and adding value to agricultural byproducts. Unlike food-based biofuels, using corn stover doesn't compete with the food supply, making it more ethical and sustainable. Bioethanol also lowers net carbon emissions because the CO2 released during combustion is offset by what the plants absorbed while growing. This helps fight climate change and support cleaner air. Overall, turning agricultural waste into fuel promotes energy independence, reduces environmental impact, and boosts rural economies, all while making use of materials that would otherwise go unused.
It all starts with pretreatment. When we process over 10,000 kilograms of corn stover per hour to make cellulose more accessible for conversion. The stover is first milled, then fed in 300 kilogram batches into steam exploder. Inside the vessel, 450 kilograms of high-pressure steam is injected, rupturing the lignin structure and separating the biomass into cellulose, hemicellulose, and xylose. This step takes just 5 minutes but significantly increases enzyme accessibility. Next comes enzymatic hydrolysis. Here, a cocktail of enzymes breaks down the cellulose into glucose over the course of 48 hours. Once hydrolysis is complete, we filter the slurry to remove residual solids, leaving behind sugar-rich liquid. This liquid then enters fermentation, where microbes convert approximately 4,200 kilograms of sugar into ethanol. The final step is distillation, which purifies the ethanol to 99%, making it ready for commercial sale.
Steam explosion is a widely used pre-churn method for breaking down tough plant biomass like corn stover before converting it into bioethanol. In this process, the corn stover is first subjected to high-pressure steam. Our process uses a pre-milling process before the steam explosion to improve the efficiency of this, allowing us to lower the operating conditions to 108 degrees Celsius and 8 bar pressure, with a residence time of only 5 minutes. After this heating phase, the pressure is suddenly released, causing the moisture inside the biomass to rapidly expand. This rapid decompression physically ruptures the plant cell walls, separating the tightly bound fibers and making the cellulose and hemicellulose more accessible for enzymatic hydrolysis. Together, milling and steam explosion are essential steps in unlocking the energy stored from agricultural waste, turning tough plant matter into a valuable resource.
Then comes the magic, enzymatic hydrolysis. Specialized enzymes like cellulase and B-glucosidase are added. These act like molecular scissors, snipping long chains of cellulose into simple sugars like glucose. The reaction takes place in a controlled environment, usually at temperatures between 45 and 55 degrees Celsius, with a slightly acidic pH of around 4.8. This is done in order to keep the enzymes working as fast as possible 24/7. In just 48 hours or 2 days, the tough plant fibers break down into fermentable sugars. Then the mixture goes through 2 filters to remove any leftover solids and separate out the sugars in the liquid. After that, it's ready for the next step, fermentation into bioethanol.
During the fermentation process, baker's yeast is used to process glucose. The yeast consumes glucose to produce ethanol, the main product, and carbon dioxide, a byproduct. This process occurs in large fermentation reactors, with batches fermenting for 3 days. The temperature is controlled to stay at 30 degrees Celsius, the ideal temperature for yeast survival. To increase process efficiency and sustainability, the initial concentration of glucose has been optimized to use less water while producing more ethanol. We also introduced a water recycle stream from distillation, which eliminates the need for fresh water to fill the fermentation reactors and allows excess glucose to be processed once more. Since the fermentation process produces over 200 kilograms of excess yeast, we will dry the yeast and use it as an animal feed additive. Fermentation also produces excess carbon dioxide, which will be pumped to greenhouses to avoid polluting the atmosphere.
The mixture of ethanol, water, and any remaining glucose and xylose then undergoes distillation to isolate ethanol from the other components. This separation method takes advantage of differences in boiling points to extract components from a liquid mixture. In this case, ethanol vapor will travel up the distillation column, while liquid water travels down, passing through trays that facilitate heat and mass transfer between the vapor and liquid. Once it reaches the top of the column, the vapor enters a condenser where it is cooled and returned to a liquid form, part of which exits the column as distillate. The less volatile components, water, glucose, and xylose, exit through the bottom of the column and are collected in recycle tanks to be reused in the fermentation step. Ethanol and water form an azeotrope at approximately 95.6% ethanol, preventing the separation of the two chemicals. The solution we developed was to use two 32-stage columns in series to produce a 94.1% ethanol product. This mixture is then sent to a molecular sieve, which will selectively absorb smaller molecules such as water into its pores and exclude larger molecules like ethanol. Ethanol will then pass around the beads and exit through the bottom of the vessel where it is collected for transport. The zeolite can be regenerated by passing nitrogen gas through the vessel at 250 degrees Celsius for 150 minutes to remove all of the water contained in the beads. This material is highly reusable and only requires full replacement every 50,000 cycles, which equates to approximately once every 54 years. This method successfully yields a 99.5% ethanol product, which meets the standards for identification as a fuel.
Based on the proposed process, 4.9 million liters of fuel-grade ethanol can be produced annually from 82.5 million kilograms of corn stover. While it doesn't appear that our process is economically profitable, the value of converting an otherwise neglected source of energy into a potential replacement for fossil fuels outweighs the impracticality of its costs. With additional government subsidies, including utilities, energy, and water usage, this process could be made economically viable. Lower purity ethanol could also be sold for other uses, such as in pharmaceuticals, cosmetics, and cleaning solutions. A lower purity would require less processing, lowering production costs and increasing profits.
Thanks
for watching! Perfect, that's exactly what I was imagining.